make sure to send your index number to the chat box, because even though it is recording, it's difficult for me to get the attendance. So please send a message of your index number. Send me a message to the chat box, right? Okay, let me share the screen. Can you see my screen?
Yes, madam.
Okay. Okay, so what we was discussing last few days about the spectroscopic techniques. So I will quickly go through these slides just to review. We talk about all the other things. I just give a summary about the spectroscopic method one. So we discussed all the electromagnetic radiations and properties of the electromagnetic radiations, and the what are the diffraction and transmission, all those things, and how the radiation interact with matter, because that is the most important thing when we talk about the spectroscopy, because in the spectroscopy what is happening, radiation interacts with the matter. And also we started to discuss the main components of the optical instruments, and there we already discussed last week the sources of radiation and the wavelength selector, monochromators and grating. So today we have to discuss the sample cells, detectors and signal processors. So we discussed these things, sources and wavelength selectors. Yes. So let's discuss other three components today. Sample, first one, the third one is the sample containers. So, right, the sample container, when we do any analysis, we should have the sample, and there should be a way to place the sample into the instrument. So in that case, we need sample containers. Most of the time, the containers can be cuvettes or cells, you know, the sample cells, and cuvettes, both are same. And also, this sample container should be made up with material that is transparent to radiation. So whatever the radiation we are using, let's say UV, IR, or X-ray, or whatever the radiation that we are using, the material of the sample container should be transparent to that particular radiation. Otherwise, we will not be able to get a signal, because the radiation is not transferred through the sample container. For example, last time also I mentioned, if we take UV, we cannot take glass or plastic cells, because the glass, or through the glass or plastic, the UV radiation will not be transferred. Therefore, for UV radiation, if the wavelength is below 350 nanometer, we should use quartz or fused silica cells. Right? And for the wavelength range in between 350 to 2000 nanometers, we can use glass silicate glasses. And for the visible range from 350 to let's say 700, 800, and for the visible range, still we can use quartz cells, and also glass or plastic cells can be used, right? And when we take IR measurement, so if we take using IR instrument, we have to use the IR region radiation. In that case, crystalline sodium chloride or KBr pellets we have to use as the sample container. So that is the third component, this main summary about what you should know about the sample container. And it plays, even though it seems sample container is really it's not, it seems like there's no much information, but keep in mind the sample containers plays a major and critical role in the spectral analysis. So based on the sample, if we get one with the wrong material, then we will not get a good signal. Right? Okay. In this figure, in this slide, I showed you some examples of the sample containers that we can use. And the very top figure, you can see the absorbance cell. I think I mentioned to you last week also, to get the absorbance, there should be, the radiation should go through the opposite walls of the cell. Therefore, the opposite walls should be clear. But for the fluorescence or phosphorescence or chemiluminescence measurement, we are using the emitted radiation. We are measuring the radiation that emits from the sample. In that case, the source and the detector are keeping in 90 degrees angle. So in here, all 4 walls should be clear in order to pass the radiation like this, right? And so normally this cell is the normal cell that we are using, standard 1 centimeter path length, the cell with 1 centimeter path length, and sometimes there are cylindrical one and microcells. Microcells are specially using when the amount of sample is really small. For example, for the standard 1 centimeter path length cell, we need at least 2.53 milliliters of the sample. But if we don't have that much of sample, then there should be a way for us to measure. In that case, we will use microcells. In the microcells, what has been done, 2 sides of the walls made like a thick walls, but the path length still 1 centimeter, right? You can see one side is 1 centimeter, but other 2 walls has been made using thick quartz or glass. And there are 5 millimeter, 1 millimeter path length cell and 20 millimeters. So different types of cell, and there's an instrument called flow cytometry. In that case, the solution or the sample should not be steady. There should be a way to flow the sample. So in those cases, this type of cells will be used. Some thermal measure, we have to conduct some temperature sensitive measurements. So in that case, we can use this type of thermal cells. And these are some examples of the sample container that we can use. Okay. Then the next component in the fourth component in the spectrophotometric analysis or any optical instrument is the radiation transducer, or we can tell it as the detector. In the very first day, I told you I will go in detail to detect those transducers, printout devices and the wavelength selector, all these things. So this is the one thing, this is another most important thing, the radiation transducer or the detectors. So what is happening here? In the transducer, it converts the information in non-electrical domains to information in electrical domains. Can you remember in the very first lectures, we discussed about the data domains and what are the non-electrical and electrical domains. So what is happening in the transducer, when we get a non-electrical signal, then it converts that signal into electrical domain or electrical signal. It may be either voltage, current, like that. So when it converts into electrical domain, then we can when it transfers to the readout device, we can get the information of that particular sample. So based on that information, we can come to conclusions of the particular sample. So that is the main role of the transducer. And in the early spectroscopic instrument, human eye or photographic plates or films has been used as the detector. So there were no any particular instrument or particular thing to detect. Instead, in the very early spectroscopic instrument, most of the cases human eye or some photographic films or plates have been used. But in the modern instrument, there are some sophisticated detectors. In that detectors, they convert the radiant energy or the radiation which is coming into electrical signal. Right. If any transducer to be ideal, there are few characteristics of those samples. The characteristics that has been listed here should be in an ideal transducer. So it should have, the very first one is high sensitivity. Ideal transducer should have high sensitivity. It should be highly sensitive to the radiation change or the incoming radiation. If it is highly sensitive, then the transducer can detect the radiation, and we will get a good signal. And also the signal to noise ratio should be higher, which means the noise part should be less. Signal should be high. And it should give a constant response over a wide wavelength range. So we are doing the wavelength scan. When we are doing the wavelength scan, the response should be constant over the wavelength range. For example, if it gives for 200 nanometers, the noise is high, and for the 300, 500, if the noise is low, then the response will not be constant. But if it is an ideal transducer, it should give a constant response, or there should not be any variation because of the wavelength. And the response time should be really fast. So if it takes longer time to give the particular signal, or if it gives longer time to convert the radiation into electrical signal, then there's no point of using an instrument. So it will become a tedious process. Therefore, the fast response time should be there. And if there are no any radiation or light, it should show a zero signal. That means the background signal should be zero when there's no any light. and the signal should be proportional to the radiant power or the strength of the radiation. So the signal should be proportional to that. Then we can get a good signal, or we can get good information about the sample. Okay, those are the main characteristics or main properties that should have for an ideal transducer. Right? Then let's discuss what are the types of transducers available. And in any spectroscopic instrument, there are two major types of radiation transducer. The first one is the photon transducers, and the second one is the thermal transducers. And most of the cases, the photon transducers are using. And what is happening in the photon transducer, the light will be convert it into electrical signal. So light will come as a photon. So we can tell photons as the light. So like energy packets, and this light will be converted into electrical signal. That is what happens in the photon transducer. And in the thermal transducer, instead of light, heat will be convert into some conduction band or something, and then it will enhance the conductivity. We will discuss some examples, then you will understand what is happening. So in the thermal transducer, because of the heat, electrical conductivity will be enhanced. Because of the heat, it will generate some electrons and holes like that, and then the conductivity will be enhanced in the thermal transducer. But in the photon transducer, the light will be converted directly into electrical signal. Right? So the photon transducers are widely used when we measure UV, visible and near IR radiation. And there's some noise, short noise. We learn about the short noise. So the short noise is prominent in the photon transducer. So that is one disadvantage in the photon transducer. But in the thermal transducer, because we use heat and temperature, therefore thermal noise is prominent in thermal transducers. Okay, so these are the two main types of radiation transducer. And let's discuss briefly what are the examples for these two types of transducer. And here I was thinking to give you an assignment. I will briefly explain the types of transducers, examples of this transducer, and you have to, I will at the end I will explain what you have to do. You have to compare maybe the advantages, disadvantages, and the operation parameters, all these things. Please go through textbooks or the whatever, any reference, and you have to make a 3 to 5 pages report about these types of transducers. Okay, I will give you details at the end. Okay, then let's go to discuss about these transducers. Photon transducer, the first type, photon transducers. So listed here are some examples of photon transducers: photovoltaic cell, photos tubes, photomultiplier tubes, photoconductivity transducers, silicon photodiodes, and charge transfer transducers. So listed here are some examples for the photon transducers, and we will briefly go through each and every examples. Okay. The first one, photovoltaic cells. So that is the very first example of the photon transducer. What is happening in the photovoltaic cell? So this diagram shows the schematic representation of the this photovoltaic cell. So in the photovoltaic cell, what is happening? Radiant energy generates a current at the interface of a semiconductor layer and a metal. You see, it's this photovoltaic cell made like a metal semiconductor metal sandwich. Can you see? There's a thin layer of silver. Silver is a metal. And the selenium, some semiconductor parts, and iron. So it's like a sandwich. Semiconductor is in the middle and it has been surrounded by two metals. So the main structure is like a metal semiconductor metal sandwich. So what is happening when radiant energy comes? It comes from this way. Radiation which is emitted from the monochromator exit slit. Exit slit of the monochromator will come from this direction, and then because of that radiant energy of that radiation, it will generate a current at the interface of the semiconductor layer and metal. So because of the radiation, it generates a current, and then that current will pass to the readout device. That is how the signal generates. So based on the power of the radiation, the signal will be changed. Right? That is simply what's happening in the photovoltaic cells. And when the irradiation happens, it produces voltage, and because of that voltage, then the current will generate. So 350 to 750 region. Basically, if we are interested in 350 to 750 nanometer range, that means in the visible range, we can use these photovoltaic cells because it produces voltage when irradiated in this wavelength range. And the maximum response will be at around 550. And compared to other photon transducers, these photovoltaic cells are less in price. So that is one advantage. And it has low sensitivity for weak radiation. If the radiation power is weak, the sensitivity is lower. It's a disadvantage. Right? So that is the photovoltaic cell. And the next one is the phototubes. So the phototubes, what is happening? This diagram shows an example of the phototubes. So what is happening in the phototubes? Here, the photon beam, you can see this one, photon beams comes in this direction, and when it hit the cathode, because of that, it generates electrons, right? And the generated electrons will go to the wire anode. There's a wire anode here that generated electrons because of the photon beam. It transfers to the wire anode. Can you remember the photoelectric tubes? So same things happen here. So electrons beam comes and it hit the cathode, and electrons are generating. Those electrons will transfer to the wire anode. Because of that electrons, a current will be generated. Then we can detect the current from the readout device. Right? So let's go to the first point. Radiation causes emission of electrons from a photosensitive solid surface. So which means when the photon or the radiation comes, cathode is a photosensitive solid surface, and then electron eject from the cathode. And wire anode and semi-cylinder cathode in a vacuum tube. So the phototube consists with a wire anode and semi-cylinder cathode. Cathode shape is like a semi-cylinder. And both these anode and cathodes has been placed in a vacuum tube. And the third point, electrons produced by irradiation of cathode travel to anode. So as I mentioned, after the radiation, electrons generated in the cathode and it travels to anode. And these phototubes have high sensitivity. So the sensitivity, if we talk about their properties, and the sensitivity is higher in these phototubes. Okay, so that is what's happening in the phototubes. Then the photomultiplier tubes. You will hear this more frequently because this one has been used widely in the instrument. So most of the cases, and I think maybe still now you are familiar with the photomultiplier tubes. So let's discuss about the photomultiplier tubes in brief. And in the photomultiplier tubes, it contains a photoemissive surface as well as several additional surfaces that emit a cascade of electrons when struck by electrons from the photosensitive area. Okay, before understand this sentence, I will go to the image of the photomultiplier tubes and explain what is happening. Okay, look at this figure, figure B. You can see the figure B. This is inside the photomultiplier tube, and there is a grill or some opening for the radiation to come, and it has this curved, we call it as dinodes. There are 9 dinodes in the photomultiplier tubes. So these dinodes has been arranged in different way. You can see the orientation is different. And what is happens now, the radiation or the photon comes through the grill. This comes from the wavelength selector. The radiation exit from the exit slit of the wavelength selector. It will comes in this direction and it will go through the grill, and it will, there's a photoemissive cathode. You can see the curvy shape cathode here. So the radiation goes and hit the cathode. If let's say one photon come and hit the cathode, then because of that photon, several electrons will be generated, and then it will goes to the dynode 1 here, this direction. Look at the direction of arrow. This is the dynode 1. Because of one photon, several electrons will be generated, and those electrons will go and hit on the dynode 1. Then after those electrons hit the dynode 1, Then again it will reflect and it will go back to the dynode 2. In that process, one electron will generate another several electrons. It's an amplification. One photon generates several electrons and hit the dynode 1. And after that electrons hit the dynode 1, then it will reflect back to the dynode 2 by generating more electrons. That means one electron in the dynode 1 will give several electrons to the dynode 2. Then again from dynode 2 to dynode 3, electron will move. When it transfer from dynode 2 to dynode 3, again one electron will give another several electrons. Same thing happen when the electrons transfer from dynode 4 to 5 to 6, 7, 8 and 9. Now when it comes to the dynode 9, for one photon, lots of electrons has been generated. It says the anode nearly 10 to the power 7 electrons for each photon. For one photon, nearly 10 to the power 7 electrons has been generated. And then those electrons will go, this is the anode, then those electrons will goes to the anode, and then the signal, electrical signal will transfer to the readout device. In the in the C, in the bottom figure, you will see there's a cathode and 9 diodes and then anode. When the signal comes to the anode, signal or the electrons comes to the anode, it will transfer through this amplifier and it will go to the readout device. Okay, so that is what is happening in the photomultiplier tube. Now think about the name. Photo. Photo means it involves photon. Multiplier tube. So one for a single photon gives multiplication of electrons, several thousands of electrons, nearly 10 to the power 7. So it multiplies the signal. So because of that, the name has been given as photomultiplier tube. Normally those photomultiplier tubes are covered using the quartz envelope like this. So that is how the names of the PMT or photomultiplier tube gets. Right? I think it's clear. Is that clear? How the electrons moves? I hope it's clear. And this figure A, the image A is an photograph of the photomultiplier tube. Okay, I just discussed the image. Then let's move back to what has been written here. Now I think it's clear. So now you know what is happening in the photomultiplier tube. Let's go to the first point. So it contains a photoemissive surface. So photoemissive surface, there's a cathode at the very beginning. It emits electrons when the radiation hits the cathode, as well as several additional surfaces, which means the diodes, that emit a cascade of electrons when struck by electrons from the photosensitive area. So it has photocathode and diodes, and it emits cascade of electrons when it when the photons hit those surfaces. Right? And this PMT, or we can abbreviate as PMT, photomultiplier tubes, these PMTs are extremely sensitive. Even with the low light, even with the low incoming light, because it multiplies the signal. So it is extremely sensitive. And light strikes photocathode, several electrons per photon. Now we already know when the photons strike, it emits several electrons. And bias voltage applied, several hundred volts, electrons form current. So you see here in this figure C, it gave some 900 volt bias voltage to the photo multiplier tube, and in between each diodes 90 volts increments. So from here to here the voltage has been 90, from here to here 90, like that. So several bias voltage has been given for this photomultiplier tube. And the electrons emitted towards a diode, 90 volt, as we discussed, 90 volt more positive than the photocathode, and electrons attracted to it. When the electrons emitted towards a diode, then the electrons will be attracted, and electrons emit towards diode, then it hit another diode, likewise. That is what is happening there. And these electrons are accelerated towards diode 2, 20 volt more positive than diode 1, like that. Each diode has 20 volts difference. And altogether for the photomultiplier tube, several hundred voltage will be given as a bias voltage. So that is what happens in the photomultiplier tube. I hope it is clear. And PMT or photomultiplier tubes are found in more advanced scanning UVs and spectroscopic instruments. So I told you most of the cases, in most of the scanning UV visible instrument, you will see these PMTs as the photon transducer. And the function is based on the photoelectric effect. So the photoelectric effect, when the electrons hit a cathode which is placed in a vacuum, it generates, sorry, not the electrons, when the photon hits the cathode, it generates electrons, and then this electron will generate a current. So that is the photoelectric effect. An additional signal is gained by multiplying the number of electrons produced by the initial reaction in the detector. So it multiplies the number of electrons. When it multiplies, the signal intensity will be increased. So that is why we call this one is highly sensitive. Okay. And each electron produces as a series of photoelectrons. So you know that one electron produces series of electrons, and multiplying its signal, thus the name PMT. So we already discussed that, how the name comes, photomultiplier tube. One electron produces series of electrons, which means multiplying its signal. That is why it get this name, photomultiplier tube. And it is very sensitive to incoming light, and more sensitive light detector in the UV-vis range. So it is more sensitive in UV-vis range. That's why I told you in the UV visible instrument, these PMTs are highly used. And long lasting, lifetime is very high, and sensitive to excessive stray light. That is one of the disadvantage. So this one is sensitive to stray light. Stray light means the light which is coming from the outside of the instrument. So other than the source light, This one is highly sensitive to stray light. That's why you will see in the UV-Vis instrument, always we open the sample container, the sample holder place. There's a, we place the sample and then we close it. So the sample is in a closed area, and it would be better if we keep this instrument away from the direct sunlight, because these photomultiplier tubes are sensitive to stray light, which is an unwanted light. So that is one of the disadvantage of the PMTs. And these PMTs are always used with a scanning or movable wavelength selector in a monochromator. So when we need to do a wavelength scan, most of the cases, these PMTs are using as the transducer, right? So those are the few important factors about the photomultiplier tubes. Any questions so far? If you have any question, it doesn't matter, you can ask, you can just interrupt me in between the lecture and ask me the question, okay? When you keep silent, I guess it is clear for all. Right. So we already discussed this figure. Then let's go to the other example, photoconductivity transducer. And still we are talking about photon transducers. And what is happening? Name also says photoconductivity, and there should be photons and conductivity should be changed. That should happen in this transducer. Because of photon, conductivity should be changed. And first point says absorption of radiation by a semiconductor produces electrons and holes, thus leading to enhanced conductivity. So there's a semiconductor in this photoconductivity transducer. When this semiconductor absorbs the radiation, look at the last point. The most widely used photoconductive material is lead sulfide. So lead sulfide is the widely used semiconducting material in this photoconductivity transducer, right? So when the semiconducting material absorb photon, you know, semiconductors has conduction bands and valence band. When it absorbs the radiation, it generates electrons and holes. When it generates electrons and holes, it will lead to electrical signal. So the conductivity will be enhanced because of the absorption of radiation, right? The conductivity will be increased. And here, the photoconductivity transducers are more sensitive for monitoring radiation in near IR range. It is sensitive for near IR range radiation, which means 0.75 to 3 micrometer. So the sensitivity is higher in the near IR range. Therefore, this type of transducers are using in measuring the near IR region. And resistance decrease when they absorb radiation within this range. When they absorb radiation within the near IR range, the resistance decrease. Resistance decrease means the conductivity is increasing. Same thing, when it absorbs radiation in this near IR range, it says the resistance decrease, which means the conductivity is increasing. That's why we are mostly using this transducers in the near IR range. Okay. Yes, that's the fourth type of transducer. And the fifth one is silicon photodiode. So it has a photodiode with semiconducting material, and this says photons cause the formation of electron hole pairs and a current across the reverse biased PN junction. Okay, let's see what this sentence means. Normally, this figure A is the schematic of a silicon diode. So this is a silicon diode. It has P region and N region, negatively charged and positively charged. So this one we call as PN junction. And when we give a reverse bias, it will form a depletion layer. I think it will not be clear for some of you. Therefore, I will explain what is known as the reverse bias. Okay, I'll go to the next slide. And okay, there are two types: reverse biasing and forward biasing. In the forward biasing, now there's normal PN junction, so it has P region, positively charged and negatively charged region, and this is the PN junction. When we apply the external voltage like this, now the positive direction, the electrons move from here to here and holes will move from this direction. Positive charge will goes towards the negative charge. That's the simply understand like this. Positive charge will moves towards the negative charge, because negative charge is here, and negative charge is moving towards the positive charge, right? So holes will move towards this direction and electrons will move towards that direction. Now the simply current will go from here to here, or electrons will go from here to here. That is forward biasing. And what is happening in the reverse bias? We change the external direction of the external power supply. And there's a mistake in this figure. I just noticed it. And we should change this one. You will see it's same. It is not correct. This is not correct. But it says positive is here and negative is there. There should be positive. If it is positive, the large line should be this side and small one should be that side, right? Make sure this image is not correct. I just noticed that. And positive should be this side, negative should be this side. That is correct, but the battery arrangement is not correct. Positive and negative. So let's see, just assume this side is positive and this side is negative. And when we apply the positive voltage here, now what is happening? Electrons are moving towards positive direction, right? So electrons in the N region will move towards this direction. And the holes in the P region will move towards negative direction, because now this side is negative. So the holes which are positively charged likes the negative charge. Therefore, holes will move towards this direction. Because of that, now the junction, in between the junction, all the electrons, there's a tendency for all holes stack in this side, while all electrons gather in this side. Because of that, there's a region with no any holes or electrons or deplete. It has some depletion. That's how the depletion layer or depletion region is formed. Now there's no any electrons or holes in between this range, right? That is how depletion region creates. When we give the reverse bias, the depletion region will create like this. I hope now it's clear how the depletion region creates. Okay, now I'm going back to the previous slide. Okay, in the silicon photodiodes, that's what's happening. In the diode, we give a reverse bias, like here, the negative charge this side and positive charge this side. Therefore, the electrons in the N region goes towards the positive charge, and the holes in the P range will goes towards the negative charge. Therefore, depletion layer will be generated when we give a reverse bias, right? So the photon causes the formation of electron hole pairs and a current across a reverse bias p-n junction. Now let's see what is happening when the photon comes. Now initially there's no any electrons or hole in this depletion range. When the photon comes, let's see what is happened. Now the depletion range or depletion layer reduce the conductance of the junction to nearly zero. Since there are no any electrons or holes, now zero conductivity, no any electrical conduction, right? In the depletion range at the very beginning. When the radiation impinges, holes and electrons are formed in the depletion range. Okay, now the radiation comes, and when radiation comes, what is happening? Holes and electrons are forming in the depletion range. Initially, there's no electrons or holes, therefore the current is zero. When the irradiation happens, now the electrons and holes are forming. What is happening when the electrons and holes are forming? Then it generates a current. When it generates a current, then we will be able to see a signal. So the current is proportional to the radiant power or the power of the incoming radiation, right? The generating current is proportional to the power of the incoming radiation, and that is proportional to the signal which will appear in the readout device. So that is how we can detect the signal or how we can detect the incoming radiation. Okay, so I think now the first point is clear. The photons cause the formation of electron hole pairs and a current across a reverse bias p-n junction. So the incoming photon, they are the main source, or incoming photons cause the formation of electron hole pairs in the depletion range, and it will create a current across the reverse bias p-n junction. Okay, and these are less sensitive than photomultiplier tubes. The silicon photodiodes are less sensitive than the photomultiplier tubes. Right. I hope it's clear. Any question? Okay, if not, let's move to the sixth example, charge transfer device. So this is again a photon transducer charge transfer device. And what is happening here, the entire spectrum can be recorded as a snapshot without scanning. So in photomultiplier tubes, we take the spectrum as when we go through the wavelength range, we scan it and get the spectrum. But in the charge transfer device, um, it is not required to scan. Instead of scanning, we take a snapshot. For example, these charge transfer devices are found in diode array. There's an instrument called diode array. It is similar to the UV visible spectrophotometer, but mainly it is using for the kinetic measurement. If I tell you how it functions, normally the UVVs, we just put the sample and we scan from the most of the cases highest wavelength to the lowest wavelength. We scan throughout the wavelength range. And when we scan through the wavelength range, we will get a spectrum in the computer or in the readout device. So it takes some time to generate the spectrum. We scan, and from one wavelength to another wavelength, we will get the signal. And at the end, we will get the spectrum. But in the diode array, there also we will get the UV visible spectrum at the end. But what is happening, we put the sample, and when we start the sample collection, what is happening, we will get a click sound and entire spectrum will pop up. There's no any wavelength scanning, right? In the diode array, entire spectrum will pop up in 1 second. So that's why I told you most of the cases these diode arrays are using for kinetic measurement. Kinetic means when we do some experiment, let's say time dependent experiment, we need to measure how the sample is changed with the time, or what is the reaction. Suppose there's a reaction undergoing in the sample container, and we want to determine how the reaction is changing, or what are the products, what is the product formation in the sample as a function of time. In that case, suppose we are doing wavelength scan. To do a wavelength scan, it takes several minutes or several seconds. Even 1 second will be enough to, even there's a 1 second, we will miss some important data. So if we use this diode array for those type of time dependent spectroscopic measurement, then within 1 second we will get the spectrum. So we will, if we are interested in lambda max, we will be able to determine the intensity or the absorption at the lambda max, right? And within 1 second, we will get the spectrum. And if we need every seconds, we can get a spectrum using the diode array. So in that case, we will not scan the spectrum. Instead, a snapshot of the spectrum will be recorded. So in those types of instrument, the charge transfer devices are using as the photon transducer, right? So that's why it says entire spectrum can be recorded as a snapshot without scanning. And the sensitivity, when we call the sensitivity, it also similar to photomultiplier tubes. So there's no any issue with the sensitivity. And integrate signal as photons drives elements. the photon strikes element, and then we integrate the signal, get the entire signal and give the signal. There are two types of the charge transfer devices, CID and CCD detectors. CCD detectors are the one of the most prominent one, charge coupled detectors. You will hear when you use the instrument, you will hear, okay, this one has CCD detector. That is one of the frequently available type. And charge injection device, CID, and charge coupled device. In the charge injection device, voltage change that occurs from charge moving between electrons. So there are electrodes. When the charge move in between the electrodes, voltage change and the signal will arise. And in the charge coupled one, charge is moved to the amplifier. There is an amplifier and charge is moving. I will not going to discuss these detectors in detail, but what you can keep in mind, there are two types of charge transfer devices, CCD and CID. Okay, so those are the photon transducers. So the 6 types of photon transducers have been discussed so far, and there are some disadvantages and advantages of these different types of transducers. So you have to discuss those advantages and disadvantages when you write that report, okay? All right, now let's move to thermal transducers. Let's quickly go through the thermal transducers. Thermal, at the very beginning we discussed that it uses heat and generate the signal. So the heat will be transferred in the thermal transducer. Instead, in the photon transducer, light is transferred or transformed. And the thermal transducers are highly used in IR spectroscopy. So IR spectroscopy is highly used. Excuse me, can you give me a second? I have an important call. I will answer this. Just give me 2 minutes. I will answer this call and get back to you, okay? Okay, sorry about that. So what we discussed was the thermal transducers. Okay, so the thermal transducers are mostly used in the IR spectroscopic technique. There's a reason. This is the second point describes the reason. Phototransducers are not applicable in IR because photons in this region lack the energy to cause photo emission of electrons. What does this mean? If you go to the electromagnetic radiation, the spectrum IR range wavelength is high, right? Compared to the visible, IR wavelength is higher. When the wavelength is high, according to the Planck's equation, E equals hc over lambda. When the wavelength is high, energy is low. Now the IR radiation, the energy is lower compared to the visible range. And this energy is not enough for the photo emission of electrons. In the photo transducers, photo emission should happen when the energy, when the radiation goes and heat, it has certain amount of energy. Because of that energy, electron emission happen or the photo emission. But this IR range, it is this IR range lack the energy to cause the photo emission of electrons. It has some lower energy, right? Because of the lack of the energy, these photo transducers cannot be used in IR spectroscopy. Instead of that, the thermal transducers are used. That's why thermal transducers are widely used in IR spectroscopic technique. And the thermocouples and bolometers are two examples of thermal transducers. Thermocouples and bolometers. Right, those are two examples of the thermal transducers. Okay, let's quickly go through this thermocouples. The thermocouple consists of a pair of junctions formed when two pieces of metal such as copper are fused to each end of dissimilar metals such as constant. So the constant, and I think it's nickel copper alloy. I'm not sure. You need to check that one. As I remember, it's nickel copper alloy or something. When this constant has been, this act as a junction, and the two copper metals will be placed like this, reference and the sample here, and the two pieces of copper metals will be placed like this, and the junction formed with a constant like this, right? And when we place the reference and the sample, now the voltage develops between the two junctions, and see here a voltage develops between the two junctions that varies with the difference in their temperature. When the temperature will be changed, and the thermocouple, right? Because when the temperature is changing, because of the difference in the temperature, the voltage will be developed. Then it will go to these all the types of resistors and the amplifiers and all those things, and it will give some output signal, output voltage VO. So that is the basic idea of the thermocouple, and this is an example of the thermocouples in normal instruments. So the thermocouple and instrumentation amplifier. This is the instrumentation amplifier. This is the thermocouple. The slit, spectrophotometer slit, means that this is the exit slit of the monochromator, and radiation comes and there will be a thermocouple junction and all the mirrors and all these things and the reference, and then it will goes like this. The radiation will, when the radiation hit, it will goes to the thermocouple junction. Radiation comes from the exit slit and it will go towards the thermocouple. Now because of the radiation, the heat will be generated, and because of the generated heat, a voltage difference will be there, and then that voltage, due to that voltage difference, it will give a signal, and the amplifiers will amplify the signal, because there should be a way to amplify signal. The generating signal is really small, and the amplifiers will be there to get the output voltage, right? So that is what's happening in the thermocouples. And the bolometer. Bolometer is also, it is a heat or the thermal transducer. What is there? It has a resistant thermometer. See this image. The resistive thermometer is there. And it consists of strips of metal such as platinum or nickel or semiconductors. So if it is a semiconductor, we call it as thermistor. If not, the bolometers are made with platinum nickel. So what is happening? The incident radiation or the radiation comes here, and there will be an absorber and the resistive thermometer and all these things, and it will give the signal, right? The bolometer. And I think I'm not expecting this thermocouple and bolometer things much in details, right? So just have a brief idea what is happening in the thermocouples and bolometers. Okay. Okay, so those are the transducers. So we discussed the two types of transducers and the examples. And as I told you, I will give you an assignment for you. So what you should do, you have to compare and contrast different types of transducers or detectors available in spectroscopic analysis. So when you do the comparison, just it would be better to have the picture. That's for sure, because if you can find the pictures, just put the pictures also, and mainly discuss structural or functional differences and the disadvantages and advantages, all these things, whether just talk about the sensitivity and like that. You can talk about those things, and I think it would be better to have it as a table. Okay, someone told me there's a power cut and battery is low. That's fine. I think I couldn't upload any recordings yet, but I will. I promise you. I promise that I will upload these recordings as soon as possible. So even if you have some power failure or anything, it's okay. No, don't worry about that. But make sure just send me your index number in the chat box, right? Then I can record the attendance. Okay. Now let's go back to the assignment. So what I told you, it would be better you have the this comparison as a table. Or I think it would be better to compare and contrast. But if you find to write it as a paragraph, that's okay. So what you need to do, understand the main disadvantages, advantages associated with them, and what are the differences in the measurement method, and all these things you can write. Okay, and the size, no need to write the lengthy report. Don't include any unnecessary details, just to the point, write it. And 3 to 4 A4 pages is enough. But if you need to include table, then you may need to use more than 3 to 3 to 5 A4 pages. That's why I mentioned here 3 to 5 A4 pages excluding tables, without tables. And font use Times New Roman. Font size, let's say 12. I will change it. Let's say 12. Times New Roman 12. And keep 1.5 line spacing. Oops. Yes, this. Okay, keeps 1.5 line spacing, and margins, that 1 inch should be enough, and submit it before, because today's 5th, I will give you 1 month. I think it's more than enough. So submit your assignment before 2nd of August. Okay, right, that's for the assignment. This assignment is for transducers. Okay, and we have one more thing left, the readout device. The 5th one, or the final one, is the readout device. So that is the easiest thing, and that is what we can see. Most of the cases, computers are the readout devices, right? And the signal processors and readouts, that's the last component of the optical instrument. So what is happening in the signal processors and readout device? Now we know from the transducer, we will get the electrical signal. So when we have the electrical signal, we are not sensitive to analyze those electrical signal. As a human or the technician, we cannot do anything with that signal. But there should be some way, some user-friendly way for us to gather or extract information from this electronic signal which is coming from the transducer. So in that case, we need to use the assistance of the signal processor or readout device. Then we are seeking the assistance of a signal processor and readout device. So in the readout device, the electrical signal which is coming from the transducer will be changed from direct current to the alternative current, or in the vice versa, alternative current to the direct current. Whatever the way, it will change the signal which is coming, and then we will get the readable and understandable information. Let's say like a graph or like anything, some readable and understandable signal we will get. Okay, so the electronic device that amplifies the electrical signal from the transducer. So signal processors also, it will amplify the electrical signal. Suppose we don't have enough signal to detect, it also has some amplifiers, and those amplifiers will amplify the signal which is coming from the transducer, or it will alter the signal from AC to DC or DC to AC. And the phase, there will be some phase transitions, phase changes also. Signal phase of the electrical wave will be changed. And also there are some filters to remove unwanted components. If there are some unwanted components in the signal, there are some filters in the signal processors to filter them out. And sometimes these signal processors will perform mathematical operations like differentiation, integration, conversion to logarithm. All these mathematical operations will be performed by the signal processors. For example, if we get a spectrum, just let's say Gaussian type UV spectrum, and we need to get the derivative. There are some options in the UV instrument. We can get the first derivative, second derivative, like that. So when doing that, when we get the first derivative spectrum, second derivative spectrum, signal processor will it will automatically process the signal. It will perform mathematical function like differentiation to convert the normal spectrum into derivative spectrum, right? So those are some functions happening in the signal processors. And readouts, most of the cases, readout device is a computer. Nowadays, in many modern instruments, readout device is the computer. So we can easily see the spectrum and we can easily extract the signal from the computer. Okay, so now, so far, we discussed the main components of the optical instrument. So whatever the spectroscopic method that you will use, there will be those 5 major components in this. So that is the basics of the basic of any instrument, right? And keep in mind, you will need, when you learn any type of spectroscopic technique, you need to have an idea. If you are learning about the instrumentation, you need to have an idea about those main 5 types of component. It is really, really important. Okay, and now let's see what are the types of optical instrument. So we discussed the components and what are the types. There are different terminologies. I will explain these terms. So spectroscope. Spectroscope means optical instrument used for visual detection of atomic emission light. So we visually detect the atomic emission light using spectroscope. And the colorimeter. So you know this one, colorimeter. In the colorimeter, human eye acts as the detector for absorption measurement. So we see the color, and in the colorimeter, normally human eye acts as the detector. And photometer. And in the case of photometers, it contains filters, no scanning function. It doesn't have any monochromators. As the wavelength selector, it has a filter. Then we call it as photometers. Fluorometers. Fluorometers are the photometers which is using for fluorescence measurement. Fluorometer. You will came with these different terms. When you further learn about these techniques, you will come up with these terms. That's why I included. And spectrograph. Spectrograph is it records simultaneously the entire spectrum of dispersed radiation using plate or film. As the transducer or the detector, it has a plate or film. So the entire spectrum will be recorded as recorded using that one. And spectrometer provides information about the intensity of radiation as a function of wavelength or frequency. So UV spectrophotometer, fluorescence spectrophotometer, likewise, it provides information about the intensity of the radiation or intensity of the signal as a function of wavelength or frequency. As a function of wavelength. So in the UV spectrophotometer, we have the absorbance as a function of wavelength, fluorescence emission as a function of wavelength, and the IR also frequency wave number, like that, likewise. So those are the types of optical instruments that you will learn somewhere someday, but I will not going to teach each of these instruments separately. Under this principles of instrumentation part, the only thing we have is to learn the basic principle of the all spectroscopic technique. But in the next section, starting from the next week after that, you will learn about the all the atomic absorption, emission, all the atomic spectroscopy and the HPLC techniques. All those techniques you will learn in detail, but I will not going to discuss in detail those optical spectroscopic techniques. So what I did was just to give you a basic idea about the instrumentation part, right? Any question? Okay, if there's no question, and no, next we have to I will discuss briefly about the mass and GC and little bit of the HPLC. I will not going to explain much details. In the mass also, I think you already learned mass spectrum, but you have not learned instrumentation part. Have you learned the instrumentation part under mass spectrum? Like the detectors and the mass analyzers, all these things. Have you learned these things? Yes or no?
No, madam.
No, yes. Okay, so you learned only how to do the analysis, how to do the structure elucidation part and fragmentation patterns, all these things you learned under mass. Here, under this instrumentation part, I will go through the basic components of the mass spectrophotometer. So let me share that presentation. Mass. Okay, can you see it now? Mass spectrometry. That slide?
Yes, madam.
Okay,
Yes.
okay. Okay, so I will go through the basic instrumentation of mass spectrophotometer. So basic components. So here we will not discuss any fragmentation patterns or any spectrum or anything. Only thing, the basic components of the instrument, right? And the basic optical instrument, I already discussed basic components, and each and every components will be discussed while you are doing the different optical instrument techniques. But even if those uh, things were not discussed, even if they were not discussed, you should be able to identify all these things when you learn each and every optical spectrophotometric techniques. Okay. All right. Let's let's go through the mass spectrometry. You already know that in the mass spectrometry, we separate ions based on the masses. And we can use this mass spectrophotometers to understand the isotopic ratio of elements. So already you know how to do those things and determine the structure of the organic molecules. So you are doing that one also. You use the mass spectral data to determine the structure of organic molecules. And these mass spectrophotometers are widely used as a detector in gas and liquid chromatography. So you will heard that in the gas and liquid chromatography, GC is for gas chromatography, LC is for liquid chromatography. It will say GCMS, LCMS. If it says GCMS, that means the detector is a mass spectrometry. In the LCMS, detector is the mass, right? So this mass spectrometry widely used as the detector in GC and LC methods. And let's discuss little about the history of this one. So people observed ions were affected by magnetic and electric field. That's how the mass spectrum came to how it originates, how the mass spectrophotometer was originated. In 1930s, Thomson, he observed this neon 2 isotope by changing the magnetic and electric field. And Dempster, in 1920s, he invented the first machine to study those isotopes. And 1942, first commercial instrument was used in petroleum industry. Now we are mostly use this for organic qualitative analysis, right? Structural elucidation. It was began in 1960s. So in 1960s, it began to be used for organic qualitative analysis, not the quantitative, qualitative analysis, like structural elucidation, like that. Okay. So the basic idea is to ionize sample by subjecting a molecule to electrical or kinetic energy. So what is happening there? The electrical and kinetic energy will be changed, or electrical energy will be applied, and the molecule will undergo ionization. And when it undergoes the ionization, fragmentations will be there. And based on this fragment, we observe the fragment pattern, and based on the fragmentation pattern, we will do the qualitative analysis. And those ions are separated based on the mass to charge ratio. Mass to charge ratio. And keep in mind, let's say if it is neon, let's say neon or whatever the element, X2 plus, and the mass of X is, let's say 20. Mass is 20, X2 plus. If the ion is X2 plus, then mass to charge ratio will be, M will be 20, charge is 2, then it should be 10, right? Keep that in mind. The reason I mentioned it, because you always use singly charged ions when you do the spectral analysis. Always the fragments, the charge of the fragment is +1, charge is 1. That's why we get the directly get the mass. But if in case if you came up with the charge 2, always remember ions are separating based on the mass to charge ratio. So you have to consider the charge as well. Right? That's why I specifically mentioned that one, because when we do the analysis, since we are doing +1, you automatically, even though we know mass to charge ratio, our mind will think, okay, if it is mass 20, x2 plus also should give mass to charge ratio 20. No, it's 10, right? Okay. Right. This is the block diagram of mass spectrophotometer. So what is happened? It will be normally the spectrophotometer will keep in a vacuum system. All these things will be placed inside a vacuum, and sample will be introduced here through a sample inlet system. Through a sample inlet system, sample will be introduced, and the ion source, it will go through an ion source. Ionization will be happen, and then the mass analyzer will analyze the masses, and it will goes to the detector. Then signal processor or computer will generate the signal. This is the block diagram of mass spectrophotometer. And what we will do, we will study each and every components of these instrument, like inlet, ion sources, what are the mass analyzers and detectors. That's the basic idea of that will be the basic thing that I will teach you. The first one, sample inlet. There are different types of sample inlet. These are the examples: batch, direct insertion probe, chromatographic one, GCMS electrospray, and ICP, inductively coupled plasma. ICP stands for inductively coupled plasma. And energy probe. These are the examples: fab sims and laser microscope and moldy. And all these sample inlets, these are the examples of sample inlets, and I will discuss briefly later in the sample inlet, right? Before that, I will go through the examples of the ionization sources. And after the samples are injected through a sample inlet, it will go through an ionization source, and the ionization happens, and these are the ionization sources available: electron impact, chemical ionization, field desorption, fast atom bombardment, secondary ion MS, plasma desorption, laser desorption, electrospray ionization, moldy. Moldy means matrix assisted laser desorption ionization. Those are the different types of ionization sources. Based on these ionization sources, we will get the fragmentation pattern. And let's say, depending on the time that we have, let's see whether we can discuss all the ionization sources or some selected ionization sources. Anyway, I will discuss the ionization sources next week. But let's try to discuss all. But if not, let's discuss some important selected ionization sources. But keep in mind, these are the different types of ionization sources available. And once the sample inlet inject the sample, it ionizes from the ionization source, then it goes to the mass analyzer. In the mass analyzer, it will separate into different regions based on the mass to charge ratio. These 4 types of mass analyzers are commonly used in mass spectroscopic measurement. magnetic sector, quadrupole, time of flight, ion trap. Right? So these are 4 different types of mass analyzers that is using. We will discuss this one also in detail. And once the mass analyzer separates the ions based on the mass to charge ratio, it will goes to the detectors, and detector give the signal. So the common detectors are Faraday cup, electron multiplier, channeltron. This electron multiplier is also similar to photon multiplier. We will discuss it later. So those are the detectors available. Right? So I will stop from here, and next day let's discuss in detail all these examples, all the detectors, mass analyzers, inlet system, and ionization source. Okay, so any questions? Was that clear? Okay, no questions? Yeah, if you don't have any question, then let's stop for today, and you can work on the assignment. But if you, while you are doing the assignment or while you are studying, if you have any concern, or if you need to clarify anything, you can email me. And I hope, yeah, if you don't have any question, then let's stop.
Thank you, madam.
Okay. Okay, then I'll wind up the session, and you will have next lecture, Dr. Lalit. I think Dr. Lalit, has he already sent you a new link? Or
Yes, ma'am.
yes, okay, good. So use that link, and probably he will start at 10:15. And okay, have a good day then.
Thank you.
Thank you, madam. Have a good day too.
I will wind up the session.